Okay, for today we were thinking what talk to give, and there are many talks about ASR, so we decided to give a brief introduction to speaker identification. But it's hard because many people here don't know much about speaker identification, but there is a group that knows a lot about speaker identification. So therefore we decided to split the talk to two parts. My is more introductory talk, and then Themos will tell you about the latest progress in the field. So what is the speaker identification or voice biometry good for? It is used in many applications. You can use it for searching audio archive, radios have audio archive on internet, intelligence agencies are using it. It can be used in call centers or banks for person identification. It can be used for some fraud detection because it's possible to see that people or one person is calling repeatedly under different identities. And in these days it is also used in criminology. Basically, there are forensic experts trying to recognize or explain if two voices are the same or not. If someone is calling, for example, mentioning there is a bomb on the train station, and so on. So, what is the main task of speaker identification? Each human body has some instruments to produce voice. There are vocal cords, cavities like mouth cavity, nose cavity, teeth, tongues, these organs, and each person have it as it unique. And so our goal is to create a model of person, let's say from inside, and we are doing it by observing acoustic waves. So how we start? We have a mic, for example, something that I have in my hand. We record this and get a waveform. From waveform, we do the same as in ASR and other tasks. Basically split the waveform to small chunks, like 25 milliseconds with some overlap, and we calculate spectrogram. So the spectrogram, you can see that it is audio, but it can be considered also to be image. Now, how to collect data? I think this is the hard part in these days, because the technology is already better than humans, so it is not possible to have some audio recordings and just label them by listening, but it is important to use other identity for the data collection. We need a huge number of speakers, several recordings for each from different environment, different nationalities, and in this, I would say there is a good job done by LDC over many years, and then there are these more recent approaches that, for example, on YouTube videos, this is Voxelab database, where the visual information is used to verify that it is really the same speaker. We have thousands of speakers, but the amount of data is still not enough. We are doing the same as in ASR and many other tasks. This is data augmentation. We are adding real additive noise, music, some people speaking in background. Reverberation is important because we need to simulate different rooms. Now I will demonstrate one architecture that, for example, Forexia was using in the product. This is a ResNet based system. ResNet is architecture very known from image processing. I have more on the next slide. What we are doing, we chunk the audio to small segments, so like 4 seconds, and actually, in speaker identification, we need to go from variation length sequences to fixed vectors. If you can see that we have this neural network that is working for frames, and then we have mean and variance pooling that is putting the frames together, and then we have fully connected layers or feed-forward neural network, and after that there is a softmax that is doing classification of speakers from our training set to the classes. I have also some technical details. This we implemented in PyTorch, and it is possible to train it on 6 NVIDIA. These are all the cards, RTX 2080 in, let's say, a week. But we don't want we would like to describe also speakers that we don't have in our training data. We do what is common in these days. We are using embeddings. So after training, we just remove softmax and the final layer, and we get speaker embedding. That is our speaker model. This is floating point vector. In our case, it was 256 values. Now about the ResNet. This network architecture, there are convolutional layers, there are 2D, two-dimensional convolutions, and you can see skip connections after each 2 layers, and there are many blocks like this repeated. In some of our experiments, we were using 34 layers, but the most enhanced or better systems use even more than 100, for example, 128. Now, one detail, but I had it on several presentations here. So what is the loss function? We are not using just cross entropy, but there is this additive angular margin loss that makes the task harder, more discriminative. And after that, we can use different approaches for scoring. The easiest way is to use just cosine distance, but in the speaker ID community also the probabilistic linear discriminant analysis is very common. How the user sees the speaker identification system. There are two parts. One part extracts the speaker model. In commercial application is often called speaker print or voice print. And then we have other module that is comparing two these voice prints and produce raw score. About probabilistic linear discriminant analysis, I like the visualization from the original paper from Simon Prince. So you can see how the model works. There are there is a mean vector, and then there is a combination of phases, or there are inter-speaker variability, and then there is intra-speaker variability and some residual noise. So you can compose the original phase or the model from these components. For scoring, we would like to have some probabilistic interpretation, and what is common is to calculate likelihood ratio. So we can have two hypotheses. One hypothesis is are the two voice prints the same, and the other hypothesis is are these two voice prints from different speaker, and we can evaluate it. So if it is through probabilistic linear discriminant analysis, it is here. So it's modeled by two Gaussians. One gives the speaker distribution, and then we can use other Gaussian to model the distribution of voice prints, and here is the way how you can calculate the likelihood ratio. Sometimes we are not having well-calibrated score, not in the form of likelihood ratio. For example, we have this cosine distance, but we would like still to have some score that can be interpreted. So for this, for example, we were using other model. Here it was logistic regression, and it was trained on some development set. So we were able to go for example, from this cosine score again to likelihood ratio that can be interpreted. Then the question is how the system works, if it works good enough or not. So we can have pairs of voice prints. We can send them to the system, and then we can have a threshold on score, and we have also the true scores, or basically if the voice prints match or not from references, and we can evaluate what will happen. So if it is the right speaker and the score is high, we are good. if it is not the right speaker and the score is low, we are also good. But what can happen? Sometimes there are not the right speakers, or the voice pads don't match, but we are getting high score. And this is for us false acceptation. And if the voice prints are supposed to match but do not match, it is false rejection. And so we can draw it in this probability or distribution of scores, and you can see that we have two kinds of errors that you would like to tune or preset the threshold based on the particular applications. So other view on the scores are dead curves. So you can see there are false alarms on one X, misses also, or for rejections on the other X, and changing basically with changing the detection thresholds, we are getting a curve. The closer the curve to the origin, the better. And this is a measure or graph that all the researchers in the field are looking at. So for deployments, there are some areas on the curve. For example, if you have a bank system and you would like to have high security, you probably prefer to have less false alarms. If you are searching for information and you would like to get all the information, you probably spend, you are okay to spend more time looking at not the matching examples, but you are getting all the right examples. Okay. One more thing, if we are in the middle, if the errors are balanced, this point is called equal error rate, and it is often used as one number for speaker ID measurement or evaluation. About evaluations, many of you heard about NIST evaluations that run for, I think, 10 years. But there are other evaluations like VoxCeleb on YouTube videos. There is short duration speaker evaluation challenge, and there are some more possibilities where you can compare the systems with others. Here I would like to show you that it is important that also the length of audio, if you extract voice prints from shorter audio, you get worse results. If you have more audio, you are getting better results. And the systems are really better every year. So you can see the big jumps, and I labeled it with the years. So the systems are really more and more powerful. Here, it's basically a nice comparison also what happened over a year with the technology. It is described in our article from BUT. So you can see that the error is really decreasing. I won't go through all the systems because I need to have some space for Themos, but we can discuss it personally if you are interested. With evaluation, for me, equal error rates and so on are sometimes hard for interpretation, but I'm getting questions what the model is really able to capture. So for this, I like this work from MIT, where they train speaker ID system to extract embeddings. They had face recognition system and were able to extract embeddings, and they were able to train some mapping function from one to the other. So here you can see original face, face reconstructed from the visual embedding, and face reconstructed from the audio, and you can see that probably the cavities that you have in your head can help to really form the shape, and you are getting at least the raw shape of your face and so on. There are other tasks like dialect identification, so probably all of this information is in the embeddings. Okay, so this was a quick introduction for the speaker identification, but people are asking very often what is the relation to fake voices and so on. So I would like to tell you a little bit about voice or speech synthesis, voice morphing, and how it interacts. So one of quite famous speech synthesis is from Google. This is Tacotron 2, and I just wanted to demonstrate what are the steps. So you can see that you have here some input text, and there is a block. It can be neural network that is creating some character embeddings. And there is other network going from character embeddings to MEL spectrogram. And then there is one more network that is going from a spectrogram and getting the waveform samples. The previous picture was simplification. Here is the real architecture. So you can see that there are more networks. It models the temporal part. There is some local sensitive attention, but it is in general you can see it as 3 steps and using new networks. But if you would like to have your synthesis speaking with someone else's voice, what you can do, you can condition one of the network by speaker embeddings. So the embeddings can be extracted from some of the systems similar to what I presented a while ago. And if you do this, you will train the new network. The system will start speaking by someone else's voice. Again, here is how it is implemented. There are the articles implemented these architectures. Here you can see there is the speaker embedding, and there is just concatenation of vectors coming from here with speaker embedding, and then you are able to change the voice. If you would like to do the real-time voice modification, you can you can change the first part, and instead of using characters, you can use some other maybe smaller units to get the embeddings, but the overall approach is about the same. What algorithms are used for deepfake or voice recognition? So very often it is neural network that is trained again to recognize basically what was changed. So we are training neural network that is getting speech signal that goes through the free neural networks, for example, to use for speech synthesis, and we have other signals that was recorded or that was not processed. And if we train such system, we can get nice results, but where is the bottleneck? In these days, we want to transfer the audio over telecommunication networks, and we would like to use as little bandwidth as possible. So we are using also digital processing, and the module is called codec, and it is again some kind of speech analysis and speech synthesis. This is one codec that is very common in these days, or it's common. It is self-based codec. There are more advanced codecs, but I would say what is the difference between this codec and, for example, the neural network-based approaches. From the practical point of view, it's the standardization. There is about 10 years for correct standardization. So in this days, or you can see that there is linear prediction here. You have some code books, and you have some loop that optimize basically the excitation. But if we want to train neural network to distinguish between this and neural approaches, the neural network can easily learn the information that is, for example, in your code book. But what is interesting, there are more modern codecs, like for example, this Google Lyra that is already neural network based, and the architecture is about the same as in speech synthesis. It gives even better results, and Google and other companies can use it in browsers where there is not necessary for standardization, where they have majority on the market. So from this point of view, we are really doing a very hard job. We are distinguishing between two kinds of synthesis, and for the fake news, we can distinguish it in this time from voice, but mainly because our telecommunication channels, the codecs are older, are standardized, but if it is voice generated by new speech synthesis and voice generated by new codecs, it is very hard. So my point of view is that the voice biometric speaker identification is really good for search. It is much better than human, but for this fake news, we need to go in other direction to track the sources and so on. So just to conclude, the speaker identification is really a task that is much better than human. In these days, we can build a really good model of human being just from distance by observing acoustic waves. And there are other modalities that are hidden in speaker's voice, like gender, age, dialects, and so on. And these modalities can be used and are waiting for researchers to attack. And now I would like to ask Themos to continue with the most advanced tasks.
Can I ask you a question?
Yeah. So maybe quick questions. And
okay, maybe we'll do quick questions and no debates. You mentioned that synthetic voices, of course, are getting very good. And then you said that some people are building neural nets to discriminate or distinguish between a synthetic voice and real voice, right? So do you know what those networks are queuing on? Where are the differences? I mean, when I listen to some of the newer synthesized voices, I can't tell that they're machines.
I would say before we were able to recognize synthesis. Now it is almost impossible to do it just by air. But if it's a new network, I think the network is able to capture the parameters that are already encoded in the speech synthesis. For example, if we speak about the cell-based codecs, there is still frame-based processing, and there is some errors caused just by this segmentation to frames. So what I see, there are many articles, and usually if you don't consider the codecs and so on, detecting neural networks work very well, but the context of the application that you would like to use it, for example, in telecommunication network or for the talk over some Teams, Zoom meetings, and so on, is not considered. Okay.
That's it? Okay, maybe we can also get questions afterward to combine, right? So, so I will present some works we did fairly recently with the Brno team, and they're about how to use self-supervised speech models, let's call them SSL, for speaker recognition and partly for emotion. Let's start by some notes. Until recently, models for extracting speaker representations did not really need, let's say, a labeled training set with respect to the speaker, right? The I vectors and the extractor was trained in an unsupervised way, right? And the first successful application of deep neural networks in speaker recognition was not really, let's build a system to do speaker recognition. It was rather than that, it was, let's take a speech recognition system, okay, and use it in a way so that it will help us assign frames to phonetic classes, rather than doing it totally unsupervised with a GMM, let's say. Of course, that doesn't mean that in order to do speaker recognition, you didn't need the labeled data. You needed for training the PLDA backend, as Petr mentioned, right? But for the main extractor, you didn't need. And in fact, that was one of the main advantages of these I vectors, let's say, with respect to the predecessor, the joint factor analysis, where you needed many recordings from each speaker in order to use them, to use the speaker in the training set, right? But things changed radically with the introduction of DNNs, let's say speaker discriminative now DNNs, right? Primarily from Johns Hopkins University, and the GALD implementation was very successful. So these X vectors provide a drastic improvement in the error rates. But on the other hand, there was no obvious way of using unlabeled recordings, right? So this was one of the motivations that was behind this approach that, which probably is one of the first, let's say, approaches to use something like a self-supervised anyway method for training an extractor, right? And it's inspired a lot by TTS models, right? That Petr described earlier, right? So assume you have, let's say, training utterance, an utterance, and you know it's only one speaker there, right? And you can extract 2 random segments from 2 to 4 seconds. Let's say segment A and segment B, whatever. And the idea is that you can somehow learn an embedding, okay, from the first segment. Okay, that's the left branch, and this will be eventually your extractor, right? And you can get this embedding and try to reconstruct the second segment. In order to do that, you need the embedding, okay, and what this person said in this second, let's say, segment. So we implemented that with ASR, so typically it's not self-supervised because we're using ASR model there, right? But there was no need for speaker labels. If you have, you can add them, and that's what we saw there with a speaker classifier. You can add them, and if you have, let's say, a portion, let's say, if a data set is labeled with a speaker, you can you can make it a semi-supervised, let's say, learning model. And so this is an encoder-decoder approach, I would say, inspired by TTS systems, right? And there were some interesting follow-ups from Johns Hopkins University that improve it in several ways by adding L1 loss also and other ideas. Now, with the introduction of the self-supervised track of Vox SRC that didn't allow the use of, let's say, other models, etc., these methods were somehow abandoned, I would say, and the community tend towards, I would say, methods inspired by computer vision. Okay, and there are a bunch of methods that came out from speaker recognition, but from computer vision, were essentially either contrastive or non-contrastive methods that where you can find, you can train some, let's say, analogous to embeddings, but for object recognition and so on. They are contrastive or non-contrastive. Non-contrastive means that you only have pairs, positive pairs, right? In the contrastive, you also need a negative pair. And these appear to be quite successful. So a typical, let's say, a typical self-supervised, I'm going backwards, sorry. Yeah, it's this way. So a typical self-supervised now method in speaker recognition goes like that. You first initialize, let's say, your extractor with one of these methods, either contrastive, non-contrastive. Now Dino has become very popular. That's the left branch there, you see. And you are clustering it with some k-means or so. You are fixing, let's say, the number of speakers to something that is close to what you believe that they are. So people know that because they're using typically the voxel lab, they know more or less that it's about 6,000, so they fix it right somewhere there. Then what you're doing is that you are retrain the classifier in a supervised way, essentially, by believing that these are the correct labels. So you're just training for some epochs, and then you're reclustering, and then you're retraining, and so on. And you do that iteratively. Okay, and this appeared to be quite, this step, iteratively, this iteration appeared to be quite successful. Yeah, but now, as you know, there is another, I would say, substantially different category of self-supervised models, okay? And this is, let's say, the family that is inspired from NLP, right? and typically implemented with transformer models. And there are also pre-trained architectures that you can download from Hugging Face, right? And for example, Hubert, you might know also Wave2Vec 2. Hubert is very standard. I'm going to go through all of it, but it has some resemblance in the sense that it does some sort of iterative train, but in the frame level, okay, and so on. I'm going to go through it. I hope you know more the basic concepts, right? And there was also this superb challenge where they're trying to evaluate these pre-trained models in several speech-related tasks. Okay, so we went through it, and the idea here is also, let me add, that you are not, at least in the main challenge, you're not allowed to fine-tune the SSL. Okay, it's the SSL, and you can add some maybe fixed, let's say, backend for this particular task. And so we went through it, and first of all, some characteristics that they have that are common. Say you want to do a task, whatever, you can, and as I mentioned, you have to keep the, let's say, architecture fixed, right? What they're doing is that they're somehow averaging all the layers, because some layers will be more appropriate for other tasks, right? So they're learning this weight average. This is the gamma there, as you see, which is essentially a vector normalized by a softmax function. And you can learn it end-to-end with the downstream task. And this layer pooling, I would say, is a reasonable operation, because all these architectures have residual connections, right? So doing such an average might not be a sensible thing to do in a standard, let's say, neural net. But if you have residual connection, it makes sense, right? So we went through these 3 tasks: speaker identification, verification, and emotion recognition, all of which are, let's say, utterance level classification tasks. And we examined a bit what they're doing. So they have typically a classification head. In speaker verification, they also added TDNN. So they're using essentially the SSL architecture as a feature extractor. And they're doing this mean and standard deviation, the standard things we're doing anyway. And in emotion recognition, also classification head. And we said that maybe this is a bit simplistic, too simplistic, I would say, because the problem here is that the SSL models are really frozen, right? And they're not obviously trained for speaker recognition or something like that, right? Maybe we can do something better than doing some sort of average first and second order statistics, right? And we came up with this correlation pooling, where you are essentially estimating the correlation between these coefficients, right? So this explains nothing more than just evaluating the correlation matrix, right? Yeah, it can be a big matrix, but you can drop the number of channels first and do that, and you can then diagonalize it, right? Vectorize the correlation, and then add one more linear layer to bring it into a 256, let's say, dimension. So we tried that, and it was quite successful, and in all 3 cases, it went really well, especially in the speaker tasks. And we have performance on par with mean STD on emotion. So the motivation behind that was some ideas, some first approaches of the style transfer. And so the idea was there, you are familiar with these concepts, right? You have an image, and you have, let's say, the image, it is a realistic image, and you have, let's say, a painting, and you want to map it, you want to transfer the style, let's say, of this painting to the image. And do that without really having pairs to train this. And there are several parallelisms you can draw. First of all, they start, in order to do that, you're starting with a model trained on ImageNet. So to do object recognition, nothing to do with style transfer, right? And in our case, we have a transformer model that is trained on, I would say, something like supervised clustering it's self-supervised, but especially Hubert, the phonetic unit, the recognition units are highly correlated with phonetic classes. Okay, but in any case, the model is not training for speaker recognition, right? And there is another parallelism that somehow they are interested in modeling and transferring the style and the texture of the image. We're interested in modeling the speaker and the emotion, okay? Both of which are somehow image or segment level characteristics, right? And so that was the motivation. Yeah, it appears that modeling the correlations helps a lot. Now, can this correlation pooling provide state-of-the-art result if we follow, because the superb challenge is quite limited in the sense that we are only allowed to train on voxel lab 1, the SSL should be frozen, it's the standard softmax, not the angular merging softmax that Petr explained. What if we do the full recipe? And it appears that it can attain state-of-the-art results, and it's either on par or better with the very standard min and STD pooling if you want to do a full training. So if you fine-tune, even if you want to fine-tune the model, the correlation pooling seems to be performing really well. And we also have another version, because you can say, okay, why not try attention there with correlation? And you can do that. All I change here is just adding this WT, okay, which are essentially attentive weights where they can learn in a standard way, right? And we tried that, and we did also some label smoothing, and we did that only for emotion recognition in this ICASP. We presented a paper, and it gave a very good boost. And these are, so far, to the best of our knowledge, the state-of-the-art results in this YEMOCAP, which is a very standard data set. And the SSL model is frozen, by the way. We are not fine-tuning at all the model. And still state-of-the-art, yeah. Now, parallel to that, we were working with BUT on another, let's say, way of extracting and accumulating information from SSL models. You see, as I mentioned earlier, many propose the use of the state-of-the-art, let's say, model, ECAPA-TDNN, and essentially replace its standard input, which is, let's say, filter banks with SSL features. But we believe that this somehow undermines the real power of SSL models, right? Because you're just turning them into a low-level feature extractor. Okay, and probably the architecture has the capacity to do speaker recognition just by a better, let's say, pooling mechanism, essentially. And in general, it's hard to train this whole architecture and backpropagate gradients, at least for us. We showed that it wasn't that easy thing to do. So we came up with this, I would say, very straightforward multi-head attention classifier. So here we are using multi-head attention for pooling, right? So you need queries, keys, and values. It's pooling, so the queries are just trainable vectors, right? Think of it like that, okay? And you can have 64 heads like that. So ideally, we want each head to model, let's say, a phonetic region, but in an unsupervised way, right? So apart from that, the only difference, the only real change with that is the following, that theoretically, or not theoretically, you should have the keys and the values, right? Now, the values should obviously contain speaker information, because these are the actual features you put, right? So these should contain, but the keys shouldn't contain speaker information, right? The keys are all, will help you to tell, okay, this frame belongs probably to this phonetic class, so you should suppress speaker information there. So we said, okay, why then do something a bit more radical than adding just a linear layer, and say that we will have a different weight average, average pooling across layers. So the keys and the values have a different way of pooling across layers, okay? This has certain similarities, obviously, with the way I mentioned earlier, where DNNs were used in speaker recognition, where you had, let's say, either bottleneck features from a DNN that is ASR DNN, and these features were helping in order exactly to do that, to assign frames to phonetic classes, right? So we did that, and we also did some other bunch of tricks, like typically you know that we are using this so-called weight decay, which is nothing more than saying, it's like putting a Gaussian prior with center of the zero, essentially, right? But here, you're starting with a pre-trained model. So does it make sense to retain a prior over zero, or the prior should be centered somehow to the parameters of your pre-trained model, right? And that's what we're doing, and it can be considered also as a simplified elastic weight consolidation way. It's just that there they have also the efficient information matrix as covariance. Anyway, so we are adding this loss, and we are also doing this layer-wise learning rate decay. So intuitively, the lower layers should, let's say, adapt in a smaller rate compared to the higher most, right? And it's quite reasonable. For example, the CNN layers, we don't even adapt them, which are the layers that are closer to the data. And with this bunch of tricks, we can show that we can have really state-of-the-art results without the need of inserting a capacity DNN, right? Just with let's say, pure attentive pooling that's very natural to the architecture, the transformer architecture, and without introducing convolutions, right? So apart from the let's say, waveform two-frame layer, which is CNN, there are no convolutions after that. Whereas with the capacity DNN, obviously there are convolutions, right? And maybe, to me, it's a bit unnatural to have a model that doesn't have at all convolutions, and suddenly in the back end, insert convolutions. It's maybe a bit unnatural. So, yeah, we show that, yeah, no convolutions are needed. Another line of research is to try adapters, right? Should we, let's say, fine-tune the whole SSL model for each task? So we tried 3 different adapters, and we experimented with VoxCelleb and CNCelleb. These are, let's say, on the left-hand side, you see just the full fine-tuning. And you have the bottleneck adapter where you're setting these, let's say, small feed-forward neural networks with a bottleneck. You have also the prefix tuning, where it's substantially different. There you are essentially learning some and prepared some frames, essentially, to the waveform. And you have the combination of this, which is a mix and match adapter. All these are implemented, we implemented, but there is a nice tool from Hugging Face that you can implement all that extension of the transformers. And so these are the results. On the uppermost in 1.5 approximately, you see what will happen if you just train the backend and keep the SSL frozen. The other horizontal line is what will happen if you do full fine-tuning. That's on VoxCelleb. And in between, you see the different adapters, and if you play a bit with the size, right? And you see the mix and match doing really well. So, okay, but now the question is, okay, but what will happen if you have a small data set as a target? So CNCelleb, for example. So long story short, we found out that what is the better approach, what's the best approach here is to say that, okay, I will fine-tune the whole network with VoxCelleb, okay, and so that to make it somehow aware of the task, right? And then use adapters to fine-tune on, for example, the CNCelleb, which is much better. So this was a better strategy, and I believe it's quite intuitive. Yeah. Finally, we experimented a bit with the whole pre-trained architecture and asked the question, okay, suppose you have the budget and the computational capacity to train from scratch SSL models. It's time? Yeah, okay. What will happen? Is it beneficial to keep it, or you can retrain from scratch? And long story short, If you are dealing with a model that is just trained on, let's say, Libre speech, and you have the capacity to retrain it on a voxel from scratch, do it. It's much better. But always retain the mask LLM style of training, okay? Do not just train it on speaker recognition. And finally, I'm running out of time, but I just want to point out that there are, in between self-supervised and fully supervised, there are other interesting methods, such as the weakly supervised methods. Okay, for example, what will happen if you don't have, let's say, the luxury of having videos, etc., as the voxel lab was created. You only have information that somehow a celebrity is somewhere talking in this recording. Okay, can you do something? Can you train from scratch a speaker recognition model? And it appears you can, and with just a relative degradation of 15%. Okay, so there are interesting applications somewhere in between the weakly supervised approaches, right? And that's all. Thank you.
So earlier there was a slide about equal error rates, and I was sort of surprised at how high they are. I'm wondering if you compare different biometrics, like fingerprints and face, face recognition, voice prints. What is sort of, how do these stack up if I wanted to build a good lock? You know, what kind of technology works?
It's better. Fingerprint in general is better as far as I'm concerned, but and face recognition typically is better, right?
So voice is the worst.
Yes. Yes.
Iris is the best. Okay.
Yeah. All right. Am I right on that? Or
I agree with this, and also you said the equal error rates are high. I would say that if they are too low, there is new database, new evaluation, because it doesn't have more sense to work on that.
So Jack Godfrey spent a whole lot of time trying to convince people that people aren't very good at this task. So you were saying the machines are better than people, but that's a kind of low bar. People aren't nearly as good as they think they are. And you know, here you were saying equal error rates of a couple %. Now maybe it's because the task is defined to be hard, so you got something to work on. But if I want to use this to decide who to put away in prison for life, I probably don't want equal error rates of a couple %. Right?
So it's true. The machine is better than human. But it's about the task definition. If you have thousands of unknown people, it's very hard to find the voice you are looking for.
Yeah, but thousands, I care about billions.
Yeah.
if I may add, you need definitely a system that is honest with what it really knows. Okay, so a system will still be useful, to the extent that it's very, very well calibrated, and therefore the probabilistic interpretation is indeed valid, that you get out of it, like a log in the form typically of a log likelihood ratio, right? And there is a lot of research towards this direction. Yeah.
I guess that you want to use voice where you have only voice, and the advantage of voice is that it's non-invasive, and it's definitely easier than DNA. It's easier than iris. It's if you don't touch anything, you don't get voice prints. But also the results here, maybe the best results on VoxelLab. What was the VoxelLab? This is less, or maybe 1% on this VoxelLab E and H, and E was. The data were already selected to be difficult, or maybe the H is selected to be difficult. So here they discarded the easy trials, and they are really just going for the difficult trials. So maybe you see here a couple of persons, but this is really on the difficult cases. the voxelab O and E. Voxelab O, I think the lowest was 0.3%, voxelab E was 0.5 or something like that. So this is where it is. Maybe it's still too high, I don't know, but it is definitely better than what humans do. And when in one of the NIST evals there was the task where the forensic experts were supposed to compare recordings, and then they were compared with the system, which are much worse than what we have these days, because it was already quite a few years ago, and the automatic system were much better than the forensic experts. They were actually advising judges during the real trials, and they were claiming that they know how to compare voices, but they were much worse than the automatic systems.
No, so what Lukáš is referring to was sometimes called the hazard experiments, the human-assisted speaker recognition or something like that, where basically you were doing speaker recognition using a machine, but humans were involved in, like, analyzing and looking, and we found that humans, just even with the use of some machine help, were terrible, and the machines by themselves are better. But there was an interesting caveat to that. It is well known that humans are terrible with unfamiliar voices, and that in the human brain, the processing of familiar voices of your parents, siblings, just follows different pathways. And while there aren't many objective studies of how good humans are, pretty much everybody can relate to identifying a close friend or relative from just one phrase after not having spoken to them for years, because the processing pathways are different. Also, Ken, I wanted to say that as far as I know, very few jurisdictions allow using voice in actual criminal proceedings. They're mostly investigative tools. So a lot of prosecutors. Yeah, no. Actually, Jack and I discussed some of these things with actual prosecutors and tried to explain to them how it's a good thing if you have somebody in your custody to sort of, say, okay, chances are this guy is telling the truth, so let him go, versus chances are it's this guy, let's keep banging on his alibi until it breaks. So they're used for things like that, but at least in the US, I don't know of any court cases where they've been allowed. Actually, Petr, do you know, do people actually present this in court for anything, or?
I think in our country it is used in courts some time to time, but it is like supporting evidence. It can't be the.
Right. Yeah. In France, actually, it's well, Jean-François is not here today, but he's often in trials in order to give an expert point of view. So the systems are not really used by the trials, by the tribunals, but actually the experts are, and so they are able. They are. Some experts are relying on the ancestral techniques, and some other experts are relying on systems, and so they have the mission to go explain how the system take the decision, to explain to the jury what is a likelihood ratio. So good luck for them. But
So the machines might be better than people, but people are used in trials, and I believe there's quite a bit of history of cases that have been reversed because of subsequent technology like DNA, and then they go back and do a postmortem and figure out how the original trial got it wrong. And one of the largest root causes of error is eyewitness testimony. That if you ask a witness to pick somebody out of a lineup, they almost always will find somebody. And the assumption is that the guilty person is in the lineup. They're not very good at reject modeling. What are you going to do if the guilty person isn't there? And then once they picked them out, their memory's overwritten and they can never get it right again, even if you show them the guilty person. And I think that this is, we could say, what are the witnesses doing? But witnesses could well be using voice and all sorts of things. I think there's quite a bit of evidence that trials do get these things wrong. And now with better technology, we could probably make, even better mistakes. Yeah.
Yeah, can I ask one technical question? It's regarding the talk by Themos, because using the attention head with some non-speaker information for the query, it reminds me of an old paper from Nico Schaefer and Mitchell McLaren back in 2014, where they use this ASR output, and then after you can, in this case they use the test query actually in order to estimate the distribution of phonemes on one side, and then look at what you have in estimate during the enrollment, and then during the test you use this in order to smoothen the distribution or to get closer to what you have in the enrollment. Do you remember this?
I remember the by SRI team, you mean, right?
Yeah.
The SRI team. The SRI introduced these methods. We followed with Patrick Kenny just a month later, right? But we introduced this idea of using in the I-vector machinery, replacing the UBM with a DNN that is trained for ASR, right? And you can either use let's say the posteriors of that, or bottleneck features extracted from that. And then Bruno had a lot of university had a lot of papers on that. You're referring to this?
Yeah, but there's an extension of this work in which they use the posteriors from the test during the posterior from the enrollment during the test, in order to modify you have your features going through, and then you weight them with the posteriors of extracted by the DNN.
I remember vaguely this
and
paper.
They make something like this. And I think that could be interesting to put it in the attention mechanism, so that you combine the knowledge, what the guy pronounced during enrollment, what do we have here, and can we trust this part of the speech because we don't observe this during the test? And
I see what you mean. Yeah, typically in speaker recognition, we want to have, let's say, something that doesn't scale with the trial, with the comparison. So by introducing this kind of stuff, you are introducing mechanisms that scale with the trial, and we don't want to have that. That's the notion of embeddings, were invented in order to avoid these things. But if you don't have any such constraint, whatever time constraint or whatever like that, you can introduce several things like that.
But somehow it's related to explainability and what the Maris team is doing, because if you have this attention weight saying, okay, during enrollment we saw that, and during test we didn't observe this phoneme, for instance, but the system gets confused because somehow the embedding is similar due to some external factor, then maybe that's a way to say, well, there's something that was here during the enrollment and not during the test. So,
yeah, we tend to believe that the embeddings are good in somehow guessing how the pronunciation somehow will be, right, of a speaker, given this, let's say, a limited, let's say, number of phones that somehow appear in these particular patterns, right? That's a whole concept of I-vectors or something. But you can also use the uncertainty, right? You can definitely use the uncertainty of the representations, either I-vectors or X-vectors, and build a more, let's say, honest LLR with respect to what you know and what you don't know, what is based on knowledge and what's based on guessing somehow, right? Yeah.
Are there stupid ways to break these locks? Like, when I was at Baidu, I think if I had your picture, I could break into the building, just put your picture in front of the camera, and it worked. Replay attacks. Yeah, replay attacks. I gather the way around that is for the system to come up with a novel phrase you have to say. But it seems like there must be all kinds of ways around these things besides just the evaluations that we're measuring. How do we defend ourselves against that?
So my opinion is basically that There are many tasks where the speaker identification is beneficial, and for example, personalization, where you have this smart speakers, that you have several people in home, and you need to get personalized answer or search in archives. So I believe that this is the future of speaker identification, and I think it will be less and less used for logs. Because I think really sometimes ago it was quite easy to distinguish synthesis and these algorithms, but it is not anymore. The algorithms are more and more complex.